place on. Let's see. Okay, that's good. Where was I? Right, so we're on the last topic of geometry. Oh, sorry, on Lewis diagram and molecular shapes and so on. And the last one that we're going to cover for today is Vesper geometry, which is short for VSEPR, or valence shell. Oh, shell is double L. Electron. Repulsion. Electron pair repulsion, excuse me. So this is the Vesper theory, VSEPR. And essentially it's just going to be a method in which we can predict the shape of a particular molecule. So for this right here, work in a group of two and grab one of these balls and put, and also take 6 of these things, 6 of the wires. We're going to get to the idea of Vesper. So you have some inkling of what they're going to be, and that way it would help you to predict the shapes and so on. So you come up there, grab a ball and 6 wires, and this is my task for you. Task number 1 is place place 3 wires on the sphere as far away as possible. So 3 wires on the sphere, and try to place them as far away from one another, and try to get 6 wires while you're at it. You just need to get 1 sphere and 6 wire, and just stick it to your seat. Yeah, 6 of the wire. We'll get to octahedral, but I'm just going to ask 3, 4, and 6, and how to place them as far away from one another. And whether we can get the geometry, which we should get. Yeah, just jam it in there and see what you get. So if you have 3 wires and put them as far away as possible from one another, what would your geometry look like? It's kind of short. That looks right. So 3 as far away from one another. Just start with 3. 3 as far away from one another. That looks right. That looks right. That one, almost there. But you get the general idea. Now I want to use, let me see what some people made in the end, and I think I got the right thing. So if you have a sphere and you put 3 wires, most of you did something along this line. 1 on one side, 1 the other one, and the other one is right across. And essentially you're going to try to make a 120-degree angle between one wire to the next, and that's essentially going to be the furthest as they possibly can. Right? Now, how about if you put 6 wires? So detach all the wires that you have on your triangle and try to put 6 wires together and try to put them as far away from one another. And see what you get from that geometry. And you can figure out how far they are from one another by looking at more or less the angles. So if you look at the angles between one wire to the next, they're as far as they could possibly be from one another, then you get the right geometry. That's number 6. If that's for 6, that's not the right one. That one's right. You can see that if I do it here, it will be perfect. So that looks right. And not quite, because you can see far away from one another. So this will go like this. This one will be trying to be further away from there, further away from there. And to do that, you just need to shift this line. Now we have evenly distributed, and they're going to be as far as they can, as far away from one another. And that makes close. This way, this one's close, this way, you rating 1, 2, 3, 4, 5. It's 5, that's correct. I don't know where to put the next one. So if you have 6 wires, most of you should have a structure that looks like this. So this is your sphere, and you have one on the top and one on the bottom, and it looks like a T, or like a square, so one across from one another. And then one of them is going to be going at the back, and the other one goes from the center out to the front, right? And essentially, if you look at the angles, it's going to be all right angle from one another. All of the angles are 90 degrees, including from the vertical side as well as the one from the side here. They're all 90 degrees from one another. And essentially, that's how you get it as far away from one another. Now, what I'm trying to get to in this particular exercise is that we're trying to imagine these particular wires as a pair of electrons. And essentially, electrons are negatively charged. So if I want to have 2 pairs of electrons, so I have, this is 2 electrons, this is another 2 electrons. If I were to put the 2 electrons here, they will try to be as far away from one another because they're both light charges and they repel. And they will try to repel and be as far away from one another. In which case, if I have 2, it would look like this. If I have 3 and I put it anywhere on the sphere, let's say over here, then what happens is that this particular one on the side is going to get close to here, so it's going to get repulsed away, so it's going to move that side. This one now is pretty close compared to here, so now there's an extra space. This one will migrate a little bit, and you get the triangle shape that you have. So essentially, if you think about these wires as electrons, and if you simply think about them that electrons repulse one another, they will be trying to be as far away from one another as possible. Then you get the point, or the theory of the valence shell electron pair repulsion theory. That is, the electron is going to be as far away as possible. Right. In which case, if you have three, then what you draw from your wires is like that. So essentially, your electrons now will have a geometry of trigonoplanar because it's 120 degrees. And if you have 6 electron pairs, then what you get is this drawing here on the bottom, or the octahedral shape, which is exactly the shape that you drew. The electron simply wants to be as far away from one another. And that's what you get from the electron pair repulsion theory. I was going to do a bit more, but I think the rest is just kind of big of a drag. But essentially, if I were to ask you to do 4, then you get this weird looking shape, which is the tetrahedral, where the atoms are, or the electrons are going to be 109.5 degrees away from one another. So that's going to be your tetrahedral shape. And again, if you look at all the wires, they're going to, which is representing as a representation of electrons, they're going to try to be as far away from one another. And if you look at it this way, you can see that they're all evenly distributed, and they are, as best as they can, as far away from one another. Hence, we get this particular geometry. Okay. Now, how is that related to the electrons itself, or the atoms itself? Well, it's mostly just kind of memorization. If you look at the shape, and you look at the number of atoms, or the electrons, and how they're distributed, you get these particular basic geometries. So let's look at one example. So let's do CH4. Right, so if we were to try to draw the Lewis diagrams of CH4, carbon prefer to have 4 bonds, and hydrogen prefer to have one. So if I were to draw this really quickly, I have hydrogen, 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 and carbon, and I give it a single bond on each. Now this is the complete Lewis geometry of CH4. But if we were actually trying to draw it three-dimensionally, we get a much closer design to this particular shape, in which case all the hydrogens and all the bonds are going to be as far away from one another. So we have a central atom of carbon there, and we have an electron here on one carbon, another electron here. Another one is going out of the board, so let me fix that drawing a bit. And the other one is going to go into a tetrahedral shape, which is this shape here. And essentially, this is your central carbon atom, and you will have some hydrogen, which is an s orbital, kind of sticking on all sides. Right? So these are the hydrogens at the end. Okay. So in terms of how to describe this particular shape of the molecules and so on, there's several different ways, which is one of them is that we can describe the shape based on the electron geometry. Which simply means how is the electron distributed, how the shape of the electrons on the central atom. Right, so in this case, what I'm referring to as the central atom is the carbon. So if I simply look at how the electron is distributed around the carbon molecule, I get this particular shape, which is the tetrahedral. Right, I'm just looking at the electrons on the carbon itself. The carbon have 8 electrons, and it's going to distribute themselves into a tetrahedral shape. Right, so now, in this case, the carbon have a particular shape, or electron geometry of tetrahedral, where the angle between them is 109.5 degrees. There's a bit of memorizations in terms of the shapes and so on, but this is what we get. The electron geometry around the carbon is going to be a tetrahedral geometry. If we were to look at the different definitions, which is, different terminology, if we were to look at the molecular geometry, now the shape that I'm interested in is not just how the electrons, is not the shape of the electrons, but rather the shape of all the atoms around the central atom, or shape of all the atoms in general in the molecule. So in this particular case, what I'm interested in is not just the carbon and the electrons around the carbon, but rather where the hydrogens are located. So in this particular case, so that's kind of the shape where the hydrogens are located, which is this one, the one over there. So in this case, the molecular geometry is also tetrahedral. So in this particular case, they're both the same. Right? The electron geometry and the molecular geometry are the same. And when I'm looking at the electron geometry, I'm just going to look at the electrons, but in the molecular geometry, I'm looking at the positions of the atoms around the atoms as well, around the central atom. In this particular case, they're the same. But I can also have a molecule where the electron geometry and the molecular geometry are not going to be the same thing. Yeah? So we'll do this one, and if I were to ask you to draw the Lewis diagrams of NH3, for example, what you will do is that for the Lewis diagrams, you have nitrogen, and you have 3 hydrogens, and as always, I'd like you to draw the Lewis diagram where the hydrogens or the atoms are clumped together in the same corner, and nitrogen prefer to have 3 bonds, and you want to get all 8 electrons in total, so the Lewis diagrams of NH3 would look something like that. Okay. Now, if I were to look at the geometry, so if I were to turn this into a 3-dimensional shape, I have a nitrogen in the middle. The electrons, you can see that there's a lone pair here, which is that one. And then I still have the same looking shape. That is, there's an electron here, there's an electron going outward, and there's also electrons going to the back of the board. Right? So what I'm trying to show here is the electron and how they're distributed around the nitrogen still look like this, but in this case there's a lone pair. I'm trying to focus the lone pair right on. So in this, yeah. Yeah. So in this case, the electron geometry is still a tetrahedral. And again, the tetrahedral shape is the one that looks like that. Right, so it's still a tetrahedral shape. But when I'm looking at the molecular geometry, I'm going to use a different color again for clarity. If I were to look at the molecular geometry, I have to take into account the fact that on the lone pair, there's no atoms attached to it. So instead, we have a shape that looks like this. We have a nitrogen, and we have, I'm going to not draw the lobe just because it's a little bit harder to draw. I'll try to draw it this way. We have a hydrogen here. We have a hydrogen sticking out, and also a hydrogen going to the back of the board. Right? So if I were simply to look at the positions of the atom itself, not the electron, I'm going to disregard this one because there's no atoms attached. So now the shape that I have is slightly different. Different shape. That's right, because there's no addition here. So in this case, the molecular geometry is called a trigonal pyramidal. And the shape that we're particularly interested in is that the electron still looks like this. So there's electron that looks tetrahedral, but I'm going to disregard the positions of the electron because there's no atom here. So in terms of the molecular geometry, the points of interest doesn't include that lone pair. So instead we just have this particular shape. And notice that there's no central atom, there's no central position there. So we have a slightly different geometry. In this case, it's called trigonal pyramidal. Now the distinction is kind of hard to see if you're looking at it for tetrahedral, which is why I'm kind of bringing it up right now. We'll do one example including the extended octet for a bit of a clarity. And I'll also try to show you how to do the extended octet with a slightly different method. And it may or may not work for you, so there's my method, which takes a bit longer. This one's a bit shorter, but sometimes it's easy to make mistakes as well. So let's try to draw the Lewis diagram as SF4 and try to determine what the geometry looks like. So if I were to do SF4, the first thing that I usually ask you to do is try to figure out the number of valence electrons. And the first step is still the same. So the valence electron in sulfur is 6, and for the fluorine, each of them is going to be 7. And I'm going to multiply by 4 because I have 4 fluorine. So 6 plus 28 is going to give me 34. So this is a slightly faster way to do the Lewis diagram as well. And instead of calculating the preferred number of atoms and so on, I'm just going to draw the sulfur. And I'm going to put the fluorine on, spread it out. And I'm simply going to count the number of electrons all the way to 34. Okay, so we have 34 electrons. So what I'm going to do first is just dispense all the bonds. So each bond counts as 2 electrons. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to give lone pairs around the fluorine because they want 8 electrons each. So it's going to be 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. But I need 34, so there must be a lone pair on the sulfur. Yeah. And this would be the complete Lewis diagram for SF4. Yeah. Yeah. I don't. The thing is, you learn what method is best for you. Counting seems to work best for me, but I know when I talk to somebody else, they just prefer to count the number of electrons like this. People like to do it that way. If you try to count it this way, it's faster, but if there's any double bond, it doesn't work very well. That's the problem. But if it works, it works. It really depends on your preference and what works for you. There's just a whole different way to get from here to Pasadena. You just choose whatever is most convenient for you. If you have a car, maybe you just want to drive. If you don't have a car and you just want to take the train and get a leisurely way, then you take the train. Depends on what you want and what you prefer to do. Now, let me actually continue with this one, and let's try to draw the shape while we're at it. So now we have, in this case, 5 things. So if I look at the sulfur, I have one is connected to the fluorine, I have another one connected to fluorine, another connected to fluorine, another connected to fluorine, and I also have a lone pair, right? So there's 5 things on sulfur, right? So I have 4 bonds and 1 lone pair, and the sum of which is 5. And this particular number is what we call the steric number. Okay. And there's 2 things that you want to know, which is, I know that the steric number is 5, and there's 1 lone pair. Okay. So steric number is 5, and there's 1 lone pair. And we can use the table of the Vespers table on the class planner to figure out what the shape is going to be. So I'm going to look at this particular table. It's called the Vesper geometry. I'm going to zoom out a bit. Okay. And what I'm going to do is I'm going to go to the one that says steric number on the corner. It says steric number, and you'll see a steric number of 5 right there. And so that means my geometry, both my electrons and molecular geometry, is going to be either one of these tables, either one of these shapes, because this is the one that says 5. Okay. So first things first, when you have 5 steric number, if you want to know, there's 2 things that we're interested in knowing: the electron geometry as well as the molecular geometry. So we can find out the steric number. So we know the steric number is 5, and the number of lone pair is 1. So for the electron geometry, all I have to do is just look at the steric number 5 and look at the first column. So steric number is 5, so which is right there. And the electron geometry is going to be this one. This is going to be my electron geometry. So regardless of however number of lone pair there is, the electron geometry is going to be always the first column. In this case, it's trigonal bipyramidal. That's because there's 5 things sticking out of sulfur, so the shape that it's going to make is this particular shape around its electron. So the electron geometry is trigonal bipyramidal. Trigonal bipyramidal. And I also know that there is 1 lone pair on the actual structure itself. Right? We have 1 lone pair and 4 fluorine. So the molecular geometry, I'm going to use a different color now. The molecular geometry, let me just go that way. The molecular geometry has to take into account both the steric number as well as the number of lone pair. So you want to look at the steric number and lone pair will give you the molecular geometry. In this case, if you look at your table, it's going to be called a sawhorse or a seesaw. I usually remember a seesaw, which is fine too. So electron geometry is trigonal bipyramidal, and the molecular geometry is trigonal, seesaws. Okay. Now let me kind of redraw the structure of SF4 to show that both the electron geometry as well as the molecular geometry. So I have sulfur in the middle, and I have 4 fluorine. So I have fluorine sticking out to the back, there's another fluorine sticking out to the front, there's another fluorine at the bottom, and there's a lone pair here. So when I'm looking at the electron geometry, it's called a trigonal bipyramidal. That's because if we highlight where the electrons around sulfur is going to be, you'll see that there's a shape that looks like this, and there's another shape that looks like that on the bottom. So that's your trigonal pyramidal. So one of each. So this is a trigonal pyramidal, but I have 2 of them, so it's become trigonal bipyramidal because there's one on the top and one on the bottom. So trigonal bipyramidal. Now, if I were simply to look at just the atoms, excluding the electrons, so I'm going to exclude this particular one for my molecular geometry consideration, then the structure that I'm interested in is just the fluorine, sulfur, fluorine, fluorine, fluorine. So in the end, I get this particular shape, which is called the seesaw. Now, if it's harder to use to see why is it called the seesaw, then if I put it on the side, it should look kind of like this, right? So sulfur in the middle, and it's called the seesaw because that's your person on the seesaw. So a lot of the time, the geometry naming is actually quite once you see the name, it's like, okay, it looks like a seesaw. While majority of them does include a lot of memorization, hopefully these kinds of things will try to relate the name to the shape while you're at it, and usually it will give you the right idea of what it's going to look like. The rest of it is just mostly memorization. You can either memorize the table, and after a while you'll actually just know it by heart. But again, it's mostly memorization. You look at the steric number, and then you look at the number of lone pair, and then you can get both the electron geometry as well as the molecular geometry. It's mostly memorization. The best practice for the upcoming exam number 4 is just going to be your lab manual, your lab report number 10, I believe, which is just entirely Lewis diagram. If you've already done those labs, then this one is like, okay, I've seen it before, and hopefully this just kind of adds to your memory a bit in terms of how to distinguish one to another, and why specifically the Vesper theory create these geometries, which is just the electrons are just trying to be as far away from one another. They repulse. That's the electron repulsion theory. So if you have 3 things, then you get trigonal planars, tetrahedrals, and so on. Any questions so far in terms of distinguishing one to the other? Yeah. No, it's not going to be in the exam, so a lot of the time you kind of have to realize it on your own. A lot of them are actually quite intuitive. If you remember a few shapes, then you'll remember one. So I usually try to remember one, and I just take out the atoms one at a time. So if I look at 4, I have tetrahedral. If I were to have a lone pair, then I have trigonal pyramidal. This is my trigonal pyramidal, and I take out one more. That's it. If I get one more, then this one is called the pentastructure, because it's pent. So sometimes there's some amusing things about it. If you draw this diagram in the end it looks like that, then well it kind of looks bad, so it's bad. So a few things doesn't require a lot of memorization. You might need to remember, the things that you might need to remember is just the difference between trigonal pyramidal versus tetrahedral, which I see quite a lot in terms of mistakes on these ones, because they kind of look similar. So tetrahedral shape and the trigonal pyramidal. So that's one. You can keep going with this one too. So if that's number 4. For number 3, we have the trigonal planar, for example. And then if you get rid of one, then you get the trigonal. Let me see if I that one was can you guys see the little? Okay, so that's your trigonal pyramidal. And because it's all triangular, and if I simply get rid of one of the atoms, then I come back to the base. So sometimes these things are easy to remember if you remember the first column. And it's a good idea to remember the first column anyway, which is the one that have 0 lone pair, because that's going to determine your electron geometry. So usually the one that you want to remember is that if it looks straight, then it's called linear, so easy to remember. The next one for 3 is trigonal planar, because it looks like triangular, and if you look at it from the side, it's flat. The next one is tetrahedral. That's the shape for the tetrahedral. Then we have trigonal bipyramidal. So we have a trigonal pyramidal on the top, and then we have another trigonal pyramidal on the bottom, so it's called trigonal bi for 2 pyramidal for this geometry. And the last one is an octahedral shape. And it is a lot of them is just memorizing what happens if I take out one, what happens if I take out another one. Another thing that you might want to do is kind of download an app. If you have an Apple or Android, you can just kind of search on it and say molecular geometry app. There's one that you can download and like, flip around, and then you can try to guess which one is which. There's a lot of practice that you can do. Okay, we are now at geometry. Any questions in terms of the geometry? We'll do one sample problem and see whether you can determine the molecular geometry and the electron geometry both at the same time. So there's quite a bunch actually. I searched it on last night and there's quite a bit. You might have to pick which one is like the best. Sometimes there's a bit more ad than there is more practice. But if you search molecular geometry, usually there's a bunch of free apps that can do that as well. Let's do one. This should be part of your lab manual. So if you want to write it down for here as well. So let's do an I3 minus. This is one of those ones that's kind of hard to do. So we'll do it the somewhat faster way, just because it's faster. So maybe I've drilled you guys the counting method. So maybe if I show it this way, it'll be slightly different. So we're going to first count the valence electrons. Each of the iodine have 7, and I have 3 of them. And there's one lone pair, so plus 1. So this is going to be 21 plus 1, so we have 22 electrons in total. And I'm going to put iodine, and I'm going to spread out the 2 iodines on the side. And I'm going to count to 22 by giving, and remember that each bond counts as 2 electrons. So I'm going to count 1, 2, 3, 4. So far I've only been using 4. I need to give it 22, right? So I'm going to give each of the iodine a lone pair on the outside. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So whatever electrons left, I'm just going to put it in the middle. That's what I'm going to do. So this is the structure that I have. And let me highlight it with a slightly different color. We have 3 lone pairs, because I have 6 lone pairs, 6 electrons in the center. So this is the one that I have now. So if you count the number of stuff attached to the iodine, you should find that there's 6. There's supposed to be 5 of them. So my 5 is 1, 2, 3, 4, 5. So I'm going to go to the column that says 5. That's kind of the way to go. So this is the column that I'm supposed to focus on. So what is the electron geometry in this particular case? Yep. Electron geometry is trigonal bipyramidal. And how many lone pairs do I have? 1, 2, 3. So 3, and go down. And what's the geometry do I have over there? Linear. Of course, if you don't have these on you, then it'd be molecular geometry is linear. Okay, and the linear because there's 3 iodine stuck to one another like that, so it's a linear geometry. It really is a game of memorization and just count. Okay, I have 5 things. 5 is electron geometry, trigonal bipyramidal, the molecular geometry all the way to the linear. Let's see. What I do want to cover for now is how do we get these particular geometries in the first place. Again, this is also going to be a memorization. And it has a lot to do with the number of electrons in the molecular orbital again. So if I have s orbital, how many electrons are there in the s orbital? 2, thank you. So s orbital have 2 electrons. If I were to go sp, each of orbital have 2, so there's 4. sp3, sp2. So let's just do it this way. So let's do an sp. So there's 2 orbital. sp2, there's 3 orbitals involved. sp3, there's 4. sp3d, because I only have 3 p orbitals, is 5. And sp3d2 is going to give me 6 orbitals involved. And I count 6 because there's 1 s, 3 p's, and 2 p's, so 1, 2, 2 p's. And essentially, if you have these orbitals and they combine together, you will get the steric number. That the steric number tells you how many orbitals are involved to make this particular geometry. So if you have 6, then the orbitals involved must involve an s orbital. So 6 orbital is sp3d2. 5, which simply means there's 1 s orbital, 3 p orbitals, and 1 d orbital. The tetrahedral is an sp3, sp2, and then sp hybridized is, I'm going to leave it out for now. Okay. So these are what they call the hybridization. Essentially, in order to get a steric number of 3, your molecule must have an sp2 hybridized orbital. In order to get a tetrahedral shape, it must have an sp3 hybridized orbital, and so on and so forth. It's a bit of memorization. It really is purely memorization. You have 4 things, then s and 3p, and so on. And essentially, it's called a hybridization theory instead of just 1s and 3p because the atoms actually, the orbitals actually combine with one another. So for example, if I were to have an s orbital that looks like that, and I have 2 p orbitals, I have 1 p orbital that looks like this, and another one that looks like that, right? But how do I get something that's spherical, something that's pointing upward, and something that's pointing to the side to give me a triangular shape? Well, the math is a bit hard because it's basically just vector calculus. But if you are a bit more mathematical, then what you have is that you have a third of an S properties, which is about 45 degree. You don't have to write this down. And then you have 2-part S orbital that's pointing outward and the other part going that way. And if you simply add the sum of the vectors, you get essentially the triangular shape. That's kind of beyond the scope of your class. But essentially, if you remember vector addition from your math class, from your geometry class, it gives you the same thing. That is, all of these 3 orbitals will combine to make 3 new orbitals that looks like that. So they will combine combine to make hybrid orbitals. And this hybrid orbital will then have the triangular shape, which is why if you have a steric number of 3, it's called an sp2 hybridization, or sp2 hybridization. That's kind of the limit that I want you to know for now, because it is kind of quantum mechanics, which is a bit beyond the scope of our class. And if you ever take advanced inorganic, then you will see this again in much greater detail. But it's just one layer of memorization. Steric number 3, you have sp2, and so on and so forth. What's more important though is the property of the sp2 and sp3 hybridized, sp2, sp3, as well as the sp hybridized. Again, it's just purely memorization. So if you have, this is the next one that I want to memorize, is that if you have a carbon or any molecule with triple bond, for example, not even just carbon, just a molecule with triple bond, what I want you to memorize is that this is going to have an sp hybridized orbital. If you have a molecule with a double bond, such as, say, oxygen with a double bond like this, or even a carbon molecule with a double bond like that, as long as there's a double bond, this is going to give you an sp2 hybridized orbital, and because this one is going to give you a triangular, so something like that. This one here looks linear because there's 2 lone pairs, that's why they're linear in terms of geometry, but otherwise it's an sp2 hybridized. And then if you only have 4 single bond, then you have a tetrahedral. Something along that line. If you have 5 single bonds, then you have trigonal biparabolas and so on. But the one to remember, really need to remember, is triple bond, sp hybridized, double bond of any kind. As long as you see any double bond, it's going to be an sp hybridized. Majority of the time. Yeah, majority of the time, because chemistry is one of those things that most of the time is true, except for these other cases. So let's just say that for now. So that's another layer of memorization that I want you to do, and the rest is just matching up the geometry and so on. Now, I'm noticing now, I was trying to get to polarity, which clearly I'm not going to be able to do because we only have a few more minutes to go. So what I'm going to do is I'm going to keep the schedule what I have on the web. So we're going to put the exams at the final day of instruction. That way we have just extra time for you to study, because I do want you to be able to draw and get familiarized with the Lewis diagram, because everything in chemistry essentially comes out to how the molecules are shaped, and whether it's polar or non-polar, it's going to give you a huge difference in terms of its property. So if you go to the web right now, you're going to find that there's going to be exam 4 on the last day of class, which is December 7th, right? So we'll keep it at December 7th, so I don't have to change the schedule again. And we have some extra time to study a bit more rather than rushing through the last day. The only last topic that we are missing for now is the electron polarity. Again, if you go to the lab, you'll have it in there as well. And what I want to show about the polarity is basically, as long as your electron is not evenly distributed, then you have a polar molecule. I already put some videos, but I'm just going to reiterate it again. So if I were to have some molecule that looked like this, for example, I know I'm pushing it for a couple of last minutes here. If I have 2 of the same molecule landed together, none of them will win electrons because they both have the same electronegativity. But if you simply have a lopsided molecule, just kind of, when you look at it, it looks lopsided, then it's going to be a polar molecule because the electron distributions are going to be different. So what I'm trying to show is that it's lopsided. So this is going to be a polar molecule. The arrows here is calling the dipole moment. Hydrogen is less electronegative than the chlorine, so the arrow is going to have a plus sign on the hydrogen, and it's going to be a positive. That means it's a polar molecule. And really quickly, if I were to have a molecule that looks like this, there's a reason why I asked you to draw the atoms of the same kind in one corner. Is this molecule lopsided or completely symmetrical? Hopefully you can see it's kind of lopsided. That is, if there's an actual atom, hydrogen is going to be here, but the bromine is going to be larger electronegativity, so it's going to be lopsided. So this is going to be polar. And it's just a really good idea when you're drawing Lewis diagram, put the same atom on the same corner, because that way you can see the polarity much easier if you do it this way. Most of the time, to determine whether something is polar or non-polar, you basically look at whether it's completely symmetrical or not. When we come back, I'm going to show you a bit more about the mole view, and just kind of a software that actually allows you to look at the mathematical projections of what the electron density exactly would look like. So for NH3, it will look something like this. So it's going to be a lopsided molecule, so it's going to be a polar molecule again. Majority of the materials are already uploaded on Canvas. If you want to watch some of the videos, they're mostly 10, 15 minutes long, I think. But we'll revisit this again on Monday, and then we'll keep the exams on Friday. All right, thanks for coming in, and then this is a